Audio working? Audio is working. I gave my face. Okay, there we go. Okay, camera's down. Don't care enough. That'll work. Okay, cool. That's not working. The mic's working though. Okay, what the hell is this thing called? Eber? Ever? Eber? Start poking things and see what works. Random string HTML. I don't care enough. How is it that I can bike home from work in 100-degree weather this afternoon, and yet I'm coming here and I get rained on?
Sprinkling outside right now.
Well, the entirety of that ramp right here is nice and soaked, so that happened fast. Oh, this is horrible. Like the entire arm into that thing, it'll move up 3 inches. Cool. It would be terrible if 6-week class we had a video hit. More than 3. Come on. There'll be 12 students remaining in the class. sense that everyone's really happy to be here and is incredibly awake. Started my first of 9 days in a row of work this morning. Going at 5:30 every day.
Good.
Didn't have to bike 6 miles to get there. I think I'd be okay. Cool. Very cool. All right, whatever. I don't care. I have 3 students. Learn stuff. And that's good enough for Ben. It's good enough for baby Jesus. It's good enough for me. Okay, so today, 4. Okay, cool. So today, I actually had intended to start off with exponents and get into roots and radicals and save everything on this list for later. And then I realized that what I wanted to do with exponents and roots and radicals in terms of algebra would require everything before that. So I realized that I couldn't really go on until we played around with some factors, greatest common factor, least common multiple, and then exponents, and everybody's favorite application of exponents, scientific notation, and then roots and radicals. Which, I mean, that's fair. I haven't written all the fancy algebraic equations for those guys yet, but I think I'm going to save that for a future class because honestly, I got enough problems already. Got enough problems and, well, examples, I should say. So yeah, this list is probably more than likely this week instead of today, because there's a bunch of stuff. Of course, we got some review stuffs. Only got 3 slides of review stuffs this time. Not a whole lot. The linear equations and expressions. So the equation was a mathematical statement equating 2 sides of an equal symbol to one another. Linear equations are equations with 1 or 2 variables, and they describe the relationship between those 2 variables. Or if it has 1 variable, it has a definite solution. That's pretty much all we're playing with right now, is those ones. So when there's 2 variables, the relationship can be shown with a straight line. So usually when you have just a straight line given, say, y equals 2x plus 1 or something like that, that has 2 variables, we only have 1 line, so there's not some magical solution for it, because literally everything along the line is a solution for it. So you end up graphing the line, which of course we'll do later. An expression is just something mathematical that is expressing something. It is an algebraic statement. So it's not an equation. So it's like saying you have 5x plus 3, or you have to evaluate one if you were told, hey, evaluate 5x plus 3 if x is given to be equal. Something like that. So that's the difference between equations and expressions. Now, of course, we're going to do one. What's terrifying about this meme is that it's true. Working at the criminal records unit, and they're still using all the old spreadsheets, and the people who designed those spreadsheets have all moved on, and nobody is bold enough to mess with any of the formulas in the spreadsheets. The entire world stands on top of it, the old Excel files. Yeah, so we got a bunch of lines on a bunch of equations. So we're gonna have some fun with them. Obviously, I felt like mixing fractions and decimals here. Now that we got a bunch of those things under our belt, I'm going to try to throw them in all the time. That way they don't get forgotten or thrown by the wayside for newer information. We're just going to keep playing with stuff that we learn. Okay. So we have 3/4 x plus 2.5 equals 18.25. Okay, well, we have 1 variable, which means we can solve for that variable, right? So our goal is to get this x alone. All right. So first thing we got to do is get this term alone. So we'll get rid of the 2.5, right? You subtract 2.5 from both sides. We're like, I don't know what that is. Okay. Ask Mr. Calculator. Got 15.75. That's still equal to 3/4 x. So there's actually, some people don't like playing with these fractions to the point that they avoid it and do this in 2 steps. That's something I avoided last time, just so you can kind of get the correct way of doing it under your belt, because we could, the correct way to do it would be to flip and multiply that fraction on both sides. You'd multiply it by 4/3 on both sides in order to cancel out that fraction, right? You end up with 12/12 and it all cancels. If you are in a test and you're freaking out. You're like, what did that weird guy that complains a lot tell me in that math class that I took that I was kind of paying attention to? And you might not remember. And if you don't remember, another way you could approach this is remembering that I told you that fractions are basically a division problem just hanging out, right? Because 3/4 is kind of a 3 divided by a 4. So one thing you could do, if you're too intimidated to do this, you're in crunch time, you're like, oh God, I don't know if that's right, I don't want to make a mistake. You could multiply both sides by 4 and then work it out. And then you would have a 3x equals whatever. 3x equals 60, 62, 63 and change, somewhere in there. And then you could divide both sides by 3 after that. That would work. And notice that that's basically what we're doing. We're both multiplying by 4 and we're dividing by 3 by flipping that fraction and multiplying it onto both sides. So both of those are correct, and you absolutely can get your answer by splitting that as two different steps. So if somebody's like, oh no, you can't do that, yeah, you can. It's math, you're fine. There's a bunch of different things you can do at any given time. Okay, well, now we got a problem, right? Because we have a decimal times a fraction. So we have a couple of options. One of them, the way I'm probably going to do like 90% of the time, is to just put this over a 1 and multiply across. I'm going to do that most of the time. Now, if I can see that I could divide this by 3 quite easily, which I mean I can. 15 goes 3 ways, 75 goes 3 ways, right? That'd be 525. And then I could multiply it by 4. So I'd end up with 21. You could do that. You could absolutely break this up, kind of like how I told you you could break it up as 2 steps before. You could break up the multiplication and the division and pick which one you want to do first. Because remember the order of operations, multiplication, division, kind of on the same level. So you can get away with that. For the moment, I'm going to go with the tried and true, and this is going to work every time way of just treating it like a fraction and multiplying straight across. Okay, so that's 63 over 3. Oh, that's nice division. I like that. 21. So we get 21 no matter which way I decided to approach that. Couldn't care less. I could split this as 2 different steps. I could multiply and then divide. I could divide, then multiply. Doesn't matter what I do. Doesn't matter how I do it. As long as I do it kind of correctly, as long as I do valid operations, whatever you do is correct. You could randomly, for no reason, have a step where you multiply both sides by 500, and then the next step where you divide off 500. And it's weird and it's pointless, but it's technically valid math and you could get away with it. So a lot of this is going to be me, going out of my way to say, hey, as long as it's valid math, I don't care how you approach it. Because there's a bunch of different ways to approach these, and there's not really one right way. Very seldomly will I tell you there is one right way to do things. And when I do, well, that means the other ways are awful. Okay. So now we have 12.5 plus 12x equals 8/16. What's the first thing that stands out to you that we should probably do?
I think 8/16.
Totally, yeah. We have 8/16 there on the right. We're looking at that and like, yeah, that breaks down real easy. right? So the first thing we could do is break that down. Everything else, let's just keep it the same for now. We're not playing with anything else, we're just doing that. Okay. Well, now I need to subtract this thing off, right? Now, I went out of my way to make sure that this would end up being a simple answer. But even if it wasn't, you might look at that kind of like the last one and being like, well, how do I approach this? Last one, I had a decimal multiplied by a fraction. Now I have a fraction subtracting a decimal. Well, you have two things you could do. You kind of want them to both be in the same terms in order to combine them. So you could either convert them both to fractions or you could convert them both to decimals. Which way is going to be easier in this case? Decimal, right? Because that we can do real quick, right? 1/2, that's 0.5. If you don't know it's 0.5, well, you punch it into a calculator, 1 divided by 2 is 0.5. So you end up with something that works out really nicely. 0.5 minus 12.5. Don't really need to calculator that, but if you do, half, and then owing 1250 against that, you are in the hole by 12. This is now a -12. Well, cool. That worked out nice, right? All we gotta do is divide both sides by 12 now, right? We divide both sides by 12. 12 divided by 12 is 1, so -12 divided by 12 is negative. Not so bad. Not so bad. Okay, let's see if I can make it more complicated, because of course I do. How would I do my job if I didn't make things overly complicated sometimes? Notice that the whole 2x plus 7 over here. Whole 2x plus 7 over here on number 3 is in parentheses. So what that's telling us is that whole thing is being divided by 4. So when I'm writing it down, I'm not necessarily keeping the parentheses, but I do have to show, hey, that whole thing is over a 4. Oh my God, what do? We want to get our x alone, right? But we have 2 of them. Okay. So if I have 2 of the x's, your first thought should be, okay, well, I have to combine those somehow, right? Because you got a bunch of things with x in a row, but you have x being your only variable, and you have an equation, which means that we really want a solution for this. So we want x equals. The other thing is, you got this weird looking fraction. So I can't really mess with anything above that 4 until that's taken care of. So what do? Multiply both sides by 4. Now, one way I could show this, I'm going to do kind of an intermediate step. I'm not normally going to show it this way. But one thing I could do, at this point, the 2x plus 7 is the same, is keep in mind, hey, I'm multiplying this entire side by that 4. Now, that means that we're going to have to distribute. And if you're iffy on the distribution property, what I recommend is put that 4 in front of a parentheses first. You can write it this way. Now, do you have to? Do you have to do that if you can tell that you're going to distribute? No, you don't have to. So that is a step you can absolutely skip. But it exists, and there it is. So you would distribute that through. The 4 times 12 would give us a 48. The 4 times the minus x will give us a minus 4x. And for the record, I have no idea what the answer is going to be because I literally threw numbers at this problem and saw what sticks. So the answer is probably weird and ugly. But that's okay. I don't really care. All I care about is getting the answer, right? Now we could go get the x's on the left side, or we could get the x's on the right side. Does not matter as long as you move all of your constant terms, all of your integers onto one side and all the things with the variable onto the other side. Either way, it's going to work out. Now, in this case, I'm actually going to move the x terms over here. And the reason for that is because if I added 4x to both sides, I would get a positive 6x. And if I do that, then that's one less negative I have to worry about. If I subtracted 2x from both sides, I would have a negative 6x, and that's just the sign that I don't want to have to worry about. I'm very paranoid about losing signs. Losing negatives in very, very large problems has instilled some certain practices in me that might, if you keep going with math, it's probably going to turn out quite nicely if you follow this way. Because I'll tell you one thing, when your problem takes 2 whole pages to fill out, and you lost a negative somewhere in the first half page, everything after it is horribly wrong. Horribly wrong. Okay, so I'm going to subtract the 7 from both sides. Going to bring it up over here because I'm running low on room. So we end up with 6x is equal to 41. Well, that's a shame, right? I think that's only divisible by 17. No. What am I thinking? I'm thinking of 51. Okay. No, 41 is just kind of hanging out. We can't break that down. So when I divide both sides by 6, to get the x alone, do I have some weird answer? Do I have some weird decimal? I mean, depends on how you look at it. 41 over 6 is an acceptable answer. It's not the destination, it's how you get there. Okay. Any questions on linear equations? Let's do a couple of expressions, and we'll move on. So we have evaluate 2x plus 5 if x is given to be 2. Okay. Well, that's not bad because that's basically saying, hey, you have 2x plus 5 and x equals 2. So it's just asking you to clean up this thing if you know the value here is going to be given by that. Thank you, Pen, for not drawing the whole way across. Okay, so do what I did before. We're going to do this, rewrite this expression, but wherever I have the x, I'm going to put that 2 in a parentheses. So instead of 2x plus 5, I have 2 times 2 plus 5. All right, well, that's not bad at all, right? We end up with 4 plus 5, 9. Okay. Well, that one was quick. Let's look at the next one. For what value of x would 6x minus 12 give the value of 60? Okay. So we're looking for which value of x that would make 6x minus 12 have a value of 60. Now you might be able to work that out off the top of your head. If I was playing around with evaluating expressions, I very well might do that. I might start throwing numbers at this, right? That's an option. However, we are asked for what x is if this is equal to that. Well, then it's kind of a stealth problem. It's not an evaluating an expression problem. It's just another problem. It's set it equal and just solve. So I had this in here largely to demonstrate that you might look at something and say, okay, well, I have some skills on how to find that out. But we might have a quicker way. We might be able to set it up as an equation and just put it together. So we would add the 12 to both sides. 6x is equal to 72. Then all you have to do, divide both sides by 6. We get x is equal to 12. No random guesswork needed. And a lot of times that's the sort of thing you would actually use algebra for, is hitting expected goals or getting different things with different variables up to a certain position. Because if I have, if you have like some random obscure quota, like say something counts as A and something counts as B, and I need to have both of them add up to like 15 by the end of the week, and we don't care versus which one is which, I might be able to set up an equation and say A plus B is equal to 15. And, if I get one, then I can figure out how much I need for the other. Stuff like that. Stuff like that is an application for this. Cool. So I've got a bunch of random percentage examples. Probably only do some of these. Yeah, we got enough time for all. We could do one. Let's do it. What is 56% of 532 to the nearest integer? That's not bad at all. We don't need algebra for that, right? Because if we're looking for 56% of something, all we need to do is convert this to a decimal. So we take where its decimal is right now and we kind of move it over twice. Add the decimal point, drop the percentage sign, and then we multiply by that number. 0.56 times 532. We end up with 297.92. So if I was rounding to the nearest integer, remember integers are basically I don't want to say whole numbers because that's its own category, but it's what we think of as whole numbers. Things that don't have decimals or weird fractions or anything. So any of the negatives, 0, or any of the positives. So the closest one would be 298, right? I usually put a little approximation symbol. I drew that symbol at enough of my my homeworks. I was taking this sort of stuff and like, if you're rounding, it's approximate. Or if you really want to get technical, anytime you throw a decimal point at something, it's an approximation. And I never liked that. The next one is if you jumble a puzzle box up and you end up with only 345 of 550 pieces. What is the percentage lost? Okay, well, in order to know the percentage that we lost, we need to know how much of it we lost, right? So you would just find the difference between the two numbers. So do the smaller, larger one minus the smaller one. 550 minus 345. That's what, 155? Help if the calculator was clear before I started typing. Oh, what am I thinking? It's 205. This is why I always punch things into my calculator, even if I'm like, yeah, I'm sure of this. I'm an idiot. I make a lot of mistakes. Make a ton of mistakes. I've never made 100% on any of my math tests because I always made at least one dumb mistake. One of them was I factored a 1/8 out of something instead of an 8. So I ended up giving 64 times the answer that way. Or a 64th of the answer that way, I should say. Okay, so we lost 205 pieces. Okay, now we need to know the percentage that is of our original. Well, in order to find that, you just divide it by the original. Throw it at a calculator. We get something interesting. It looks like it's 0.37272727, blah, 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 blah. The 27 repeats forever. Okay. All right, well, if I need to switch that to a percentage, I'm going to take this decimal point, move it over twice. But how do I represent this? Well, on a problem like this, normally you'd be asked to round or something, right? In this case, we have a asked to round. Would I round just based on what I think? Well, I mean, if the 27 repeats forever, I might just round it to 2 decimal places, or maybe even 3. I could do 0.273. I could do that. I could put 0.27 and put that bar over it. That implies that it goes on forever. There's a lot of different ways to represent that answer. So which way is correct? There's no specific correct answer. Depending on the problem, you might say that this is 37%. You might say that this is 37.273%. Or the 37.27 that goes on forever. It basically just depends on the context. Now, since I like to be as correct as possible, that 0.27 that has a bar over it implies forever. Is that the actual answer? Yeah, that kind of covers us out to, like, you know, even a billion decimal points, right? So I kind of like that. However, I will give you the heads up that a lot of times you won't see that very often, that symbol, little bar. You don't see that very often. You might see that in different types of math, maybe accounting. There's math in biology, stuff like that. Maybe even chemistry. I don't know. I didn't take chemistry. I am awful at it. But there's a lot of different applications of all of these concepts, and it just depends on the context. Okay. Let's do more. I love doing more. We're all very happy to do more. Okay. 16% of your side job's paycheck is taking out, leaving you with $145 for 2 weeks. What was the paycheck? Do I smell food or am I having a stroke?
Smell food.
There's food.
Someone passed by.
Want their food. If they have pizza, I'm going on a raiding party. I'm just gonna paint my face. All right. By the way, outside is dry again. It was soaked a little while ago. Now it's dry. All the water is already dried up. I love it. It's ridiculous. Okay, so we have 145 for 2 weeks, which is a pointless point of the problem, because we don't care how long it goes, right? What are the useful points of this problem? That it's 16% that was taken out, and we have $145 left. That's important, is that we have 145 left. That is after 16% came out. Okay, so those are important pieces of information. And it's always very important to keep in mind kind of what the direction of the percentage is, like what it's directed at. Because 16% was taken out. Instead of the 145, can I take 16% of 145? No, right? Because the 16% of 145 is probably very different from 16% of what we started with, right? So you always have to keep in mind that it's a percentage of what. I always like to look at word problems with percentages, and I always like to ask myself what the percent is being applied to before I go any further, because that is one of the most common mistakes I see. So we have 145 left after 16% is taken out of, we don't know. We don't know, so we don't know how much we made. So I'm gonna say that's our X, our original paycheck, that's our X. Okay, so let's kind of map this out. Let's say we had 100% of our X. And then a little bit got taken away. We took away 16% of X. And then we ended up with that 145. Okay. Well, that works out nicely, right? That translates directly to an equation. Because we can say, okay, well, what's 100% as a decimal? Well, you move the decimal over, right, by 2, and you get, oh, it's a 1, right? 100% as a decimal is just 1. So I don't have to multiply 1 by X. That's just going to be X. Minus 16% of X. Well, move that decimal point over, we get 0.16 of our X. That's still equal to the 145. Now, could I have approached this differently? Could I have said, hey, if I have 100% and I'm taking away 16%, what do I have left? And then make my equation? Yeah, I could have. But then we wouldn't have this wonderful situation here, because this always scares people. How do I subtract it if I don't have a number out front? Well, we kind of do, right? There's basically a 1 there. So if you run into this situation and you're like, oh God, how do I subtract these? How do I put these guys together? Just kind of think of that 1 that's It's not really there, but it's there, you know? Because how many X's is that? One, there's an X there, right? Okay. Well, what would that be? Uh-oh, 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 just clear the whole thing. All right. 1 minus 0.16, 0.84. So we have 0.84 X is equal to 145. Oh no, I like that, right? Because that we could just divide off. We divide the 0.84 on both sides. We get this weird looking thing. 172.619, and I bet, yep, I bet it goes on forever. Some weird lack of repeating. It actually probably, yeah, it totally does repeat. 619047, 619005. It just rounded that. It would have been 47. So it actually repeats those 6 digits forever. Remember, if it can be written as a fraction, then the decimal is going to repeat. Doesn't matter how ugly it is. Doesn't matter if your calculator goes out that far, the decimal will repeat. Is that useful to know? Might come in handy sometime. I don't know. But all I know is that big, ugly, repeating decimal, it's a dollar amount. Dollar amount, how far do I have to take it? Second decimal, right? So I have 172.619, blah, 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 blah. I don't care. All I care about is the pennies. So we're going to say it's 172.62. Isn't that fun? Oh, so much fun. Oh, so much fun. We're having so much fun with these. Let's do 3 more. Yeah. Those of you online can't see everyone in person, but everyone's face just lit up with joy. Joy and excitement. All right. So you miss out on a sale and the price jumps back to 700 from 460. What percentage was the sale for? Okay. Well, we don't care that it's over. We care about working out what it was. Things that are useful in that problem, well, that it's back up to 700, which means that was the original price. You always, if you're playing around with percentages, you want to know which one was your original amount, which one's your 100%. So it'd be that 700, and it went down to 460. Okay. Well, if we're taking a percentage of 700, then we need to know what our loss is, right? So very similarly to the earlier problem, we're just going to subtract those, figure out what the difference is. Be 240. But I've been up too long, so I don't trust me. 240. And we need to know what percentage of that is of that. Okay, divide them. And again, I really like doing that. Not only does that make me think of smaller numbers, but it's also easier to type in, right? So 24 divided by 70, yes, I could reduce it further. No, I don't care because I am getting a percentage, so I need the decimal. And I get this fun looking thing. Okay, I'm gonna write that down for now. 0.342857. Probably goes on forever, I don't care. So we need a percentage. So we're gonna move it over twice. Well, it's 34 points. How far do we feel like going? Doesn't really matter. I always like 3 decimal places. So here, here, and here. We'll have a 2, an 8, and that 5 is gonna have to round up, right? So 34.286%. That is an obscure percentage. Why would you put anything on sale that much? Just do 35%. 33%. Doesn't matter. God, it's like some bored math guy just threw this together. Didn't even work out the problem to try to make the answer make sense. Because it doesn't have to be a good answer. You just got to get the process down. Speaking of random processes and me being bored, Bill Murray got bored and got a part-time job working at Starbucks. He's given a raise from $11.50 an hour to $15.45 per hour. What is the percent increase he's gotten while still regretting his voice acting job in Garfield? Really, that shouldn't have happened. Legend says that he thought it was directed by the Coen brothers. Because his agent said, hey, do you want me to try to get you a job in this Coen movie? He was like, absolutely. He didn't know it was spelled a different way and that it had absolutely no relation, and it was a god-awful movie. Random obscure fact, when they made you guys remember that really old Ghostbusters cartoon where it was always supposed to be the original guys? It totally wasn't. The guy who voiced Bill Murray in that was the same guy who voiced Garfield in the Garfield cartoon. So when he took that crappy movie, I thought it was just this weird loop closing. Yeah, I have no life. All right, so 1150 is going to 1545. What percentage increase do we got? Well, percent increase works exactly the same as percent decrease. We need to know the difference, and we need to know the percentage of the original. So, big one minus small one. You know what? We could even, let's make a funky fraction out of this, because we're going to end up dividing it by our original one, right? Let's just write it that way. In fact, if you ever look at, say, financial math books or something, and they're trying to teach you percent increase as being their own method, they'll have a fancy looking formula for that. But we just kind of pulled that out of the air, right? Cool, that's like 90% of the math books for things that aren't algebra. Literally just pulling things out of the air. I had to tutor somebody in accounting once. I never took accounting, and I looked at it and I was like, oh my God. Why do you have 4 pages of spreadsheeted charts of these numbers when literally all you need is one equation? You are multiplying this number by this number and getting that. You don't even need to look it up. Oh no, we're not learning it that way. Why? Would make everyone's life easier. So that's 395. That's a good raise. I like it. Oh, people have been complaining about 15 an hour for so long, but 15 an hour ain't gonna cut it for anybody. Okay, so I got weird decimal again. That's okay, because I'm going to do the exact same thing to this as I did the last one. I'm going to take that decimal, move it over by a couple. I'm just going to round it to 34% because I don't care. Why not? If you want to, you can absolutely go as far out as you want to. Both answers are correct. This one is more correct, and that is a very unfortunate concept to attach to anything, is that one thing is more correct than another, but both are correct. Let's do one more and then play with new stuff. Or old stuff. Let's do new stuff. New stuff. You have driven a car off the lot. Values immediately change from 23,500 to 6,500 since it's now used. What is the percentage decrease in this sad reality? Never liked that idea because they kind of have to drive it onto the lot. You know, it's not brand new. It's been driven. Don't give me that. Always remember being a kid and my dad tried to sell one car to a dealership while he was getting another one. And we were there for hours because my dad wouldn't budge on trying to get the blue book price. Which I get it, it's fair, but also, you know, they're going to resell it, so they're looking at it for a profit perspective, and they're probably going to shoot for getting at least that blue book price. They don't want to just give you a hug and say thanks. Okay. So we got 23.5 going to 6 and 5. All right. So we're finding the percentage decrease, exact same concept. We're going to find the difference and then figure out what that is out of our original. You know what? Let's do this again. Kind of like that. That worked nice, right? I'm so tempted to do something that I haven't gotten to yet.
Good. Good shortcut.
Well, the shortcut is we're about to learn factor. Everything's got 2 zeros at the end. So if I pull out 100, then that 100 could cancel with 100 down here. You'd end up with 235 minus 65 over 235. And that's easier to type, and you can get away with that. If you don't like it, well, it ends up being the same answer with a couple of zeros on it. We end up with 170 over 235. Thank you, good calculator, for giving me a simplified fraction. Apparently it's 34/47. I don't care. This is going to be 0.7234 and change. So move that over a little bit, and it's 72.34%, which seems about right. Kind of what happens. Why I like the idea of used cars. That's also why the only car I've ever owned for a little while before it got destroyed didn't have working windows. They didn't roll. Didn't even get a chance to take the doors apart. Cool. How we feel about percentages and linear equations and stuff. How we feel about stuff. Are you feeling okay? Horrified? Slightly screaming inside? You feel okay. That's good. I'm glad you feel okay. That makes one of us. All right. Let's do new stuff. I like new stuff. New stuff isn't old stuff. Hi, new stuff. So new stuff goes pretty nicely. And actually the main, one of the main reasons that I covered the basics of algebra so quickly in this class is because I really wanted to be able to do factoring. That's actually an extremely useful method with linear equations. And I haven't gotten to cover it yet. So now we're going to cover it. Isn't that great? Actually don't have any problems for it today, but it will show up in the future. Okay. Actually, I just kind of did one of those problems, huh? If factored, did it necessarily make our lives easier? Debatable. Okay, so factoring is the process of breaking down a number or expression into its smaller factors. Factors are numbers we can multiply together to get another number. The factors of 6 would be 2 and 3. It's, things that multiply together to get 6. So prime factorization is a little bit different from that. That's actually the process of breaking down a number into smaller composite numbers and finally all prime numbers. So you are literally breaking it down as far as possible. In the example of 6, well, it's still 2 and 3. Okay, it's a number 6. Not a whole lot goes into that, right? So to understand this, we first need to understand what prime numbers and composite numbers are. And I will give you the heads up that the phrase composite numbers, not really going to pop up a whole lot. Not going to pop up a whole lot. But knowing what a prime number is, that's useful. In fact, you'll use them regularly. You don't even need to remember to call them prime factors. They're just things that don't break down any further. A prime number is a whole number greater than 1 that cannot be made by multiplying other whole numbers. It is divisible only by 1 and itself. So basically, it's when you get, you're breaking something down, you get to 17, and you're like, what goes into 17? Nothing nicely, right? Okay, cool. So 17 is a prime number. Same with 2. Is 2 a prime number? Yeah, because the only things that go into 2 are 1 in itself. So a composite number is just what we call a number that's further divisible. So it's composed of more prime factors. So like 6, that's a composite number because you break it down further. And then I like to add a little bit at the end here about the number 1. And prime numbers are defined that way for a reason, right? 1 is not considered to be a prime number. They have to actually be divisible both by 1 and themselves, but they have to be 2 distinct numbers. So 1 is divisible by only itself. It's technically not a prime number or a composite number. So what's this useful for? Knowing when you're done. You're not going to break something down into 1s or anything like that. You're just going to go down to the regular prime numbers and call it good. Okay, so how to find the prime factorization of a number. It's actually pretty simple. Thought about deleting these next couple of slides. Didn't. So you start working from the smallest prime number you can think of and start kind of dividing them up, right? So you have a 12 and you think, okay, smallest number I can think of that goes into that, 2. Okay, so you divide it by 2. All right, so we get a 6. All right, so the next thing you do is what's the smallest number that can go into 6? 2 again, right? So you get 3. Okay, so you divided by 2 twice, and you ended up with a 3. That means that the prime factorization of 12 is 2 times 2 times 3. Now, don't be frantically making notes or anything off of this because this is not the way I prefer to do it. Because honestly, that would just take forever. So if it doesn't go down by 2, then for the example here of 147, you try the next prime number, 3. Okay. So 147 divided by 3 was 49. Hey, 49 I recognize. 7 would work. We know that 7 times 7 is 49. If you don't, well, I highly recommend memorizing all the perfect multiples up to, like, I don't know, 11, 12. Did you do 13? Was that 169? I don't really care. Up through 12. Those are the ones I use the most. I haven't cared about anything higher than that, so that's usually what I do. So you just kind of break it down until you get the prime factorization. So that method works when you can clearly see what a number is divisible by. Sometimes it's just easier to break things down into primes by breaking into multiple composites. Like 90, I might say 9 and 10, and then I would break down the 9, and then I'd break down the 10, right? So what I prefer is the tried and true factor trees. I hate teachers that don't use factor trees for this because honestly, it's not an easier way. I prefer easy. I prefer ways that I can't make a horrible, stupid mistake. So if I can avoid making a stupid mistake, I'm going to do it. Factor trees are the way I like. So 48, you would think of any two numbers that it could break down into. So in this case, you have 8 and 6. You break the 6 down to a 2 and a 3. You break the 8 down into a 4 and a 2. The 2 doesn't break down any further, but the 4 does into another 2 and another 2. You end up with 4 2s and 3. So you just kind of take all the prime factors across all the bottom branches and call it good. Let's do a bunch of them. I absolutely don't want to do 12 problems, so we're not going to. We're not going to do 12 problems. Do number 1, like number 1, it's 100. It's a nice round number there. That's good to start on. Let's break it down. You have a couple of options. You can do 10 times 10. You could do 2 times 50. You do 25 times 4. Literally whatever you want to throw at it. I don't care what you want to throw at it. Doesn't matter. Literally doesn't matter because whatever you put down below it, if it's a composite number, it's going to break down further, right? So we get 2 and 5 and 2 and 5. Yeah. Well, you just write them. I like to write them in kind of ascending order. So small numbers to big numbers. I regret opening this far. Why does this take so long? And that's it. Let's do some more. Let's do I don't know. I don't like any of these. These are all too simple, right? These are all too simple. I don't like any of them. Let's have fun. Let's just make some fun problems. Let's do yeah, there we go. Let's do 980. I like that better. All right. Because the method that they always teach you is, oh, obviously I know that this breaks down to this and this. I hate that because what about the numbers that are obvious? Am I going to look at 980 and say, oh, obviously this goes in? No, right? Now it ends in a 0. So you know what? I love just breaking off that 10 right away. That's nice, right? So all I really do, then I can break down real nice. All I really do is throw stuff at it and see what sticks. Now 98's nice because it's even. And if it's even, that means 2 goes into it. In this case, it goes in 49 times. 49 is 7 times 7. There we go. 2, 2, 5, 7, and 7. Let's do some more random problems. Let's do some more numbers off the top of Ben's head. I like this. This is working a little nicer. The examples aren't the greatest. Let's do 288, like 288. I didn't give myself enough room for 288, but it's gonna get messy. I'm gonna flip to the other side of the page here. Didn't give myself enough room for 288. Okay, 288. I don't know what goes in there, but I know it's even. Okay, so I'm just gonna divide by 2. 2, and I get 144. Now, at any point, if you recognize something that'll break down nicer, you can. If I don't recognize 144, I'd have to keep going, right? That is a perfect square, however. So, let's say I don't know that. That, we're going to divide it by 2. What do I get? 72. Oh my God. What about that one? I can do a couple of different things. I know that's how many hours there are in 3 days, so I could do 3 and 24. That's an option. I could chop it in half. You know, spoiler alert, I'm going to chop it in half. And I would end up with 36. That's an option as well. I like that because I know 36. 36 is a number I'm familiar with. That's 6 times 6. And each of those breaks down into a 2 and a 3. We've gone as far as we need to with that concept. What do we got? 1, 2, 3, 4, 5 2s. So many 2s and 2 3s. Cool. Do we feel like we're okay with factor trees?
Equations.
Oh, don't worry. Because you're gonna love the application for this. You're gonna love the next slide. Okay. Let's do one more example. One more example. Let's do (1050) a squared b. Let's throw some letters in here. I like throwing letters in things. Always freaks people out. And it's like, no, it's not bad. Because the number part you do the normal way. Number part, you're just going to ignore all of that stuff until the end. Okay, I'm going to do my usual. Take the 10 off the end. Look at this and say, hey, that's divisible by 5. Ends in a 5, right? So if it's divisible by 5, divide them both, you end up with 21 here. Oh, can't forget that 10. That would be bad. We got 2, 5, 5, and 21 so far. 21 breaks down to 3 and 7. So what do I got? Well, a 2, a 3, 2 5s, and a 7. Well, what about those letters? Well, what's a squared mean? It means I have 2 A's. And then what do I have here? Well, that's just a B. So I got an A, I got an A, I got a B. Yay, effort. Yeah. I think those were better examples than doing 12 really slow, really slow factor trees, right? Let's move on. To greatest common factor. Now, in the course of my tutoring, which I started as a tutor at WNC in 2008, so it's been a while. And I always could say, I told people for a long time, I could teach a monkey calculus. I could teach you guys calculus, no problem. But the one thing that I always found really annoying was finding a good way of explaining greatest common factor. Because you kind of gotta see it, you kind of gotta understand it, and then be able to pull it kind of out of the air. So in order to make these lessons, I had to go hunting for different methods on finding greatest common factor and then least common multiple. The method I ended up with on the following slides, not my favorite. And when we get to those problems, I'm also going to show you how I like to do them myself. And maybe you could put those two together at some point or pick one versus the other. But I'm going to kind of show you a foolproof method of doing it and the, I don't know, not foolproof method that I prefer. And the reason that I prefer the not quite foolproof method is because what we're going to do for these is very difficult. And by very difficult, I mean, honestly, it's just time consuming. We make charts. I don't like making charts. I'm not a big fan of making charts. So conceptually, greatest common factor, which is very often broken down to GCF, is the largest factor that 2 or more numbers have in common. As a check, both numbers are perfectly divisible by the greatest common factor. For example, between 10, 20, 30, 40, 50, and 60, all of those numbers are divisible by 10, right? But they can't go over that because 10 can't be divisible by any number bigger than itself, right? I can't divide all of these by 20. 20 wouldn't go into 10, it wouldn't go into 30, and it wouldn't go into 50. So you look for the biggest thing that they all would have in common evenly across the board. So in this case, the greatest common factor is 10 because 10 fits into all of them, right? Every one of those is divisible by 10. The simplest example of how we've already used this is simplifying fractions. 2/4 is an example of a fraction where both the numerator and denominator are divisible by 2. Once you divide both of them by 2, the fraction simplifies. That's one of the main uses for greatest common factor. I can definitely say in much higher math, watching things just start to cancel out and get simpler, it's like, oh, thank God I'm getting there. The finish line is within my grasp. So as I put down there, later greatest common factor is especially useful in factoring larger expressions in algebraic functions. It's extremely useful in cleaning up larger problems. I found one thing that I didn't erase the other day. Did I end up erasing it? I don't remember if this was applicable or not, but I found something that I was like, I could terrify my students with this. Yeah, that. I could terrify everyone with this. Hey, look, it's calculus. You know, the nice thing about the limit form of a derivative in calculus, all of this is algebra. Is it nice algebra? Nah, not really. But it's really satisfying when things start canceling out. So that's something the greatest common factor ends up being really, really useful. Basically, this is where the distributive property backwards thing comes back. Okay, so you're gonna have to bear with me for this explanation. I know a few people online have already taken me before, so you've probably seen it. You're probably like, oh God, not this again. Nope, we're going into it. So there are multiple ways of finding the greatest common factor, including simply playing around with the numbers. You can totally do that. Worst case scenario, that's kind of worked for me pretty nicely. The simpler method is to list the prime factorization of all the numbers involved and select all factors that are common to all the numbers. So if you look at 15, 30, 45, and 90, well, you might be able to figure that one out just based on the numbers. But if you can't, you break them all down. So 15 is 3 times 5, 30 is 2 times 3 times 5, 45 is 3 times 3 times 5, and 90 is finally 2 times 3 times 3 times 5. So you take those, kind of put them in order smallest to largest, and you line them up with each instance of the factor, giving a column to itself. Subsequent numbers using that same column first, then adding a new column whenever a factor is repeated. So I'm personally not happy with how I typed this out. Let's fix it. Fixing it can make our life easier. Well, do I already have this as an example? No, cool. Let's fix it. I don't like this. And here's how I like to do this. For number 15, you just, the first one you got, you just write out, right? So you have a 3 and a 5, okay? Now 30, we look at the prime factorization. I'm lazy. 2, 3, and 5, right? And every time you have that number already, we have 2, 3, and 5, right? Well, we already have a column for 3 and 5. So we reuse those columns. And since we don't have a column for 2 yet, that's where that guy goes. So now we have 30 is 3 times 5 times 2. And then 45, go back a little bit, 45 was 3 times 3 times 5. Okay. So we already have a common column for 3 and already a common column for 5. But we need another column for a 3, right? But we don't want to take that one. That one's already taken. So we skip it. So we make a new column for that 3. So now we could see 45 is 3 times 5 times 3. Okay. And then 90 is 2, 3, 3, and 5. Oh, well, we already have a column for all of those, right? We have one of the 3s, the 5, the 2, and finally the other 3. All of those kind of fall into place that way. So once you have them arranged in these columns, what do they all have in common? The 3 and the 5, right? So that's what you end up doing. Copy this. We're going to break my last slide. Whoa, what did I just do? Bear with me. There we go. Hi, little fella. Let's drop you down. What size are you? 18? Okay. So this is where you would look at this and say, okay, what do we have in common? The 3 is in common on all of them. The 5 is in common on all of them, but not that 2 and not that 3, right? So you multiply together what you have in common on all of them, and you'd say, okay, 15. The way I had it before, it looked nicer, but it's totally not how you end up working it out. So that bothered me the last time I taught this class, and I was like, I'm going to fix this. Then I forgot. Now I fixed it. So this method is one of many, but it's the most concise method I've found that doesn't result in large rooms for error. But always necessary line them up perfectly. No, it's entirely up to you as long as you can tell what's in common across our numbers. However, this method is also just as useful to demonstrate least common multiple. More on that, which is, believe it or not, 2 slides from here. Okay. We got stuff. I love stuff, right? Let's do a bunch of these. So probably already guess what the greatest common factor is going to be, because it can never be any larger than the smallest number. That's probably 50. But let's do the method anyway, because I can. So you find the I can speak today. You find the prime factorization of each number. Okay. And then what we're going to do is we're just going to make our weird little chart. First one's always the nicest, 15. It's 3 and 5. The next one, 30, already has, we already have columns for the 3 and 5. But we don't for the next number, which is the 2. And then the next one, 105, is 3, 5, and 7. Oh, we already have the 3. We already have the 5. We don't have a column for a 7, so we make one. If you're writing these down, leave a space underneath, because we are totally going to come back to this problem. Assuming that I didn't have that as an example here. I did not. Okay. So what's in common across all of them? 3 and the 5, right? Now you might say, Ben, I hate this. This is a very, very weird way of doing these things. To which I would reply, I know, I also hate it. I saw this many, many years ago. Someone in the tutoring center was explaining it this way. And it took me a while to wrap my head around it. And I was like, I hate this. Why don't we just eyeball? That's really hard to teach. Really hard to teach eyeballing math, right? What can I do? Well, I could look at this and say, what do they all have in common? They all have this 3. They all have this 5. Cool, 3 and 5. You could do that. That works. I like that. But doesn't quite translate to least common multiple, which is the next method. At which point that's harder to eyeball. Which is why I've decided on this method, because I figured out that I could teach both of these things. Why no? Were you copying? See you know. I don't know what I wrote now. Did I ask a question? Am I talking? I don't remember what I say. You need that? Is something need that? Need that? We like. We not. I have a photographic memory. I'm moving. Okay. Number 2. Why did I just do 2 numbers? I don't like that. Why do I keep doing 30? I don't like that. Let's do throw another number out there. What number do we want? Anybody got a number off the top of their head? Not small. Huh?
180.
180? I like it. I like it. That's actually a good one. Oh, she said 17. I am not going to use 17. That is going to cause a problem because 17 is already prime. And I don't want to deal with that. You know what? Why not? Let's also do 17. Oh my God, what did I just do? Oh, there's a print button on this keyboard. Oh my God. All right. Well, it doesn't have a printer configured, so that's good. I would totally just write on a sheet of paper, come find me. If you play around with the printer settings, you can usually remove the header and the footer from the printer, you know, where it usually has like the page title and all that crap. You could totally just freak somebody out that way. Like when I took a year at Oregon State, and girl down the hall didn't realize that her weird little print server thing that she bought was totally just giving the whole dorm Wi-Fi. Oops. Totally printed to a printer. It's great. Imagine just sitting at home and your printer just starts talking to you. Okay, so we're gonna prime factor all of this. Why did I just say the 15 was 2 times 3? I'm very tired. Very tired. As I'm tired, I am prone to making mistakes. If I make a mistake and you notice it, you're like, why did you do that? He must know what he's doing. Please tell me. I don't know what I'm doing. $180, that's 2 times 90, which is 2 times 45, which is 5 times 9, which is 3 times 3. Good number. I like it. 5 prime factors. Solid number. Okay. So, actually, it's a really bad idea to include the 17. It's a terrible idea to include the 17. Cool. Well, let's do one with 17 and one without. I'm going to put the 180 here. I'm going to put the 17 at the end. Since that's just going to end badly. Oh, not LCD. GCF. Hey, if you had a fraction and these were all your denominators, this is how you could find the lowest common denominator. It's literally the exact concept. Actually, no, I have that backwards. LCM, that's the next thing we're doing. I'm losing my mind. Sorry, guys. Ben's tired. All right. So, I always like to start off with my smallest number here. So we have 2, 2, and 3. Okay. And then the next one we have a 30. Am I using a pen? Yes, I am using a pen. What's wrong with using a pen? What, you don't like to do your math in pen? I always did. This is an erasable pen though, for the record. So 30 is 2, 3, and 5. Well, we have a column for a 2. We have a column for a 3, but we don't have a column for a 5, so there we go. 180, we got 2 2s, 2 3s, and a 5. Well, we got 2 columns for 2s, 1 column for 3, 1 column for 5. So we need another 3, right? Okay, here's the problem with 17. 17's prime. So if I tried to find the greatest common factor between all of these, with that 17 included, there isn't one. That's the problem here. That's the problem. I am, however, going to, let's cross that out for now. Because we do have the greatest common factor otherwise, right? Skipping the 17, these 3 would have 2 in common, and then 3 in common. The greatest common factor in this case, why did I put a 0 at the end? Oh man, I'm tired. We end up with a 6. Again, I'm going to totally leave a little space at the bottom of that one because when we hit the next concept, I want to come back to this page. How are we feeling about this so far? Horrified? That looks like a horrified, but I don't want to say it face.
No, it's going awesome.
Okay, I don't believe you. Okay, so for the next one, 24, 168, and 40. Well, break them all down as far as they'll go. 168, that's 2 and 84. which is 2 and 42, which is the answer to life, the universe, and everything, which is 2 times 21, which is 3 times 7. Thing I like about factor trees is it doesn't really matter if somebody tells you, hey, what's the prime factorization of this horrifying 6-digit number? We're just going to start off dividing by 2 until we can't anymore. And then we're going to start dividing by 3 until we can't anymore. And you just keep doing it until you're done. Okay. Now, if you want the shortcut way of doing it, just circle what's in common on all of them. This one doesn't have a 3. Don't care if these two do. So our greatest common factor would be 2 times 2 times 2, which is 8. I like this way of doing it. Ben, why don't you do it this way? In case you get confused about least common multiple. That's why. So that's kind of the other way around. So 24, we get 2 times and 3. 40, we get 2 3 times. They're already represented. And a 5. It gets its own column. 168. We have those 2s, a 3, and a 7. So your greatest common factor is what they all have in common, multiplied together. Okay? How are we feeling on this method? Feeling okay? Anybody online struggling? See you, chat box. I see one person in chat box. None of the rest of you like me. Nobody else is talking to me. Feel my judgment. Hey, I don't blame you. So let's move on from this concept and play around with one of its uses. So if you look at 6, 7, and 8, well, they're not too bad, right? Because we've done these sorts of things before. Hey, I'm kind of popular. I'll take it. People just like me for my math. When I grew up, looked in the mirror, knew I'd have to be funny one day. And you know what? Didn't pull it off. Why did I just write the last one? Hey, look, we got problems. All right. So the general idea is to find the greatest common factor and reduce, right? So what's the largest thing that 12 and 30 would have in common? Hmm? 6. Yeah, right? Because we could see that 6 goes into 12 twice, and 6 goes into 35 times. Now, notice how I phrase that, how we look at this. 6 goes in here twice, and 6 goes in here 5 times. So it breaks down to 2/5, right? If it had broken down that way to something that was further reducible, then we wouldn't have found the greatest common factor. We would have found a common factor. And like I said, here in the test, you have to simplify something. It is entirely fair to, chop it in half and then say, hey, 3 goes into those and break it down further, right? But if I have to do that multiple times, I didn't find the greatest common factor between the two numbers. I found a common factor. I found a common factor. By us using the 6, that was the greatest common factor. It was the largest thing they have in common. So 12 and 30, that's doable, right? What about 24 and 40? Do we know that off the top of our head? We have an idea, right? 8, yeah. Okay, does it work? Let's find out. So 8 goes in here 3 times, and 8 goes in here 5 times. That doesn't reduce. So yes, that's exactly what we want to do. Okay, how about 196 over 462? Anybody want to take a stab at that? Well, I mean, you can't just eyeball that and say, oh, obviously it's 6. Obviously it's this number, that number.
88.
Huh?
88.
I don't know. Nope. So, what do you do? Well, factor them both separately. Okay, 196. Gotta be cheap about this. 196 and divide it by 2. Okay, it's 2 and 98. And divide that by 2. Hey, it's 2 and 49. I like that, right? That's 7 and 7. Okay, 462. That's 2 and 231. I don't have a clue what goes into 231. Do you guys? No. So instead of trying a 2, let's try odd numbers. Let's try a 3. 77. All right. I like 77 because I could see an 11 in there. 711. All right. Cool. So what do they have in common? A 2 and a 7. 2 times 7, 14. So both of those numbers are reducible by 14. So normally you would just cross them out and divide it, but what I'm going to do, I'm going to write it this way just for note purposes. It's good to divide them both by 14. Hey, you know what 196 divided by 14 is? The other ones? 2 and 7, 14. Hey, you know what 462 divided by 14 is? The other ones? 3 and 11, 33. That's one nice thing about factor trees. If I'm dividing these two off, everything I have left, just everything I have left, right? Cheap, but it works. Which is 100% how I like to teach math. Cheap, but it works. So that's a useful application of greatest common factor at this point. I want to algebra this. I don't want to algebra this. Haven't done exponents yet, but we could get away with some basic exponents. Let's play with stuff. Don't write this down yet. I might change it as I go. Let's do, yeah, I kind of like it. Kind of like it. Kind of like it. This is a more realistic approach of something in math that you might use greatest common factor for, because the most frequent thing you're going to do is you're going to use it to break down large algebra things into smaller algebra things, things that you can very nicely plug things into. So if you have, you got to think, say that you're dealing with, say a job where you have to figure out the pressure in a line, and that line gets fed through multiple different areas with different factors attributing to it. You might end up making some horrifying equation of the pressures in the system. At that point, you start playing with physics. But you work that out, and then you start noticing that things can cancel, things can break down. So you break things down as far as you can go, and then you have something neat and concise and simple that you can just use from then on. And that might be, again, plugged into a spreadsheet for the smart people to never touch again, because that's pretty much going to be the effort involved. That's the sort of thing you would see applications of this. A lot of times, you might end up doing just the work once. Might be outside your pay grade, might not be, but if the engineers do it to make the building that you're standing in, it seems to work out pretty nicely. Unless the building collapses, then it didn't work out pretty nicely. So you would look at this, and essentially what we have here as a fun little algebraic hint of the future. If I have two terms adding together, it just kind of gets called a binomial because there's two terms. So it's binomial. If there's one, it's a monomial. If there's three, it's a trinomial. If there's four, that's where everybody stops numbering them and they're just polynomials. There's a bunch. In case like this would be referred to as a complex fraction because you got stuff happening in a fraction. So we want to break this down. We want to make this not suck, right? So what you might do is you might say, look at both of these terms on top and say, hey, what do they have in common? Well, they each have a 5 in common, right? And they each have an x in common because this x squared means that this is x times x, okay? So they both have an x in common. So what we're doing is we're going to factor this. We're going to pull out the 5x from each of these guys, and then we're going to write what's left. So if I pulled out a 5 and one of those x's, what would I have left? One left, right? If I pulled out a 5 and an x here, what do I have left? Well, the x is gone. 5 out of 15, that'd leave you a 3, right? So we end up basically dividing the common factor off of both of them. Okay. Now, one of the very, very important parts of algebra is that Here's a random example off to the side. If you have x plus 3 divided by x, if you do this, that's a no-no. I write no-no on it. That's a no-no. You can't just cross out into something because this is a number plus 3 divided by that number. If that number was a 5, I can't say 8 divided by 5 breaks down to a 3. That wouldn't work. You broke math. So one of the things you can't do is you can't chop into things that are added or subtracted. But once things are broken down into factors, like this parentheses here, even though it's got 2 numbers added together, I can't simplify that any further. So that is a factor. A factor. So I have a factor times big ugly factor that I'm not going to worry about, divided by a factor times a factor. Well, if I got multiplication division happening, I could certainly cancel there, right? So we can cancel this out front with this. So the 5 goes into itself once and into the 24 times. And x divided by x just kind of disappears. If it was a 2, then 2 divided by 2 is gone. If it was a billion divided by a billion is still 1, so it's kind of gone. So what do we have left on top? Well, the 5 and the x are both kind of not there, right? We have a 1, but 1 times that thing, it's just that thing. So I don't really need that set of parentheses there. There's nothing acting on it, so it doesn't have to be separated out. So we can kind of drop it. Down here, we have a 4 left. All that's hanging out there, that's what we got. So that is more of an algebraic example of what you would use greatest common factor for. Now, there's a whole lot of other factoring rules when it comes down to it in algebra, but we're not playing with those today because, well, I don't want to melt your brains. And that just seems mean. This seems mean. I haven't done a difference of squares in a while, so it'll be a while. Trinomial or any of that stuff. Okay. I like that I put a 9 on there. I don't have a 9 in my example. It's a random example. Whatever. I don't care. How do we feel about greatest common factor? We can apply it, right? It's doable. It's kind of weird when you get higher up there, but that's okay. We're mainly worried about the concept, right? Let's do more weird stuff. I love new weird stuff. Let's do more weird stuff. Okay, so least common multiple is basically the other way around. So we found the largest common factor between 2 or more numbers, right? That's what we did. We found the biggest thing that went into a bunch of stuff, right? So least common multiple is kind of the other way around. You have a method to find the least or lowest common multiple between 2 or more numbers. So we already kind of know how to do this, right? So if I was adding fractions, say I had a fraction of 1/3 plus a fraction of 1/2. I was adding them together. Got a 1/3 and a 1/2. What would I have to make the denominators to add those together? Because they got to beef up, right? They got to go to the first thing they both go into, which is 6. Well, that's exactly the concept here. You are finding the first thing that all of your applicable numbers will actually go into. Okay. So my example there. Oh, cool. I use the exact same numbers that I just pulled out of thin air. I use 2 and 3 a lot, don't I? All right. Oh man, I still have this one written terribly. All right. Hold on a minute. Da, 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 da. Okay. So the easiest way I can explain least common multiple is to use the exact same method that I used for greatest common factor. So in this case, we're using the exact same numbers that I used as an example, 15, 30, 45, and 90. They all factor exactly the same way. They all break down exactly the same way. And then the next one's the one I have to fix. Da, 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 da. Oh man, look at that. I already fixed it. Isn't that great? Like I'm a ninja. So up until that point, the methods are exactly the same. But the least common multiple is effectively a number that comprises all the factors of each one of our terms. So if 30 has a 2 in it, then the smallest thing that they could all go into has to have a 2 in it somewhere. If one of the numbers has a 7 in it and the other one has 2 7s, well, in order to cover all your bases, you would end up going with the 2 7s. So what ends up happening is you actually take one number from each and every one of our columns. So, for example, hi, little fella. Remember him? I remember him. He had a random 17. Let's assume that 17 is still there. Let's do another line. But this time, we're just going to find the lowest common multiple. Because we've already done the work for all these numbers, right? Well, lowest common multiple would comprise all of your factors. So whereas this one was just what they have in common, this one would be everything. One thing from each and every column. Let's throw 17 in there just for funsies. Hi, 17, you finally got to make it. This was your big break. Look at that. Now, what is that number? I don't know, but it's going to suck. 2, 2, 3, 5, 3, 17, 3060. So that is the smallest number that all 4 of these would go into. If there wasn't a 17 there, it would be 180 because both 12 and 30 go into 180. So, you know, that's fine. But I felt like throwing the 17 back. Okay. What about that? Did that one pretty easy, right? Same idea. If I was finding the lowest common multiple, 2, 2, 2, 3, 5, 7. It's exactly the same method. You break them down exactly the same way, do the columns exactly the same way, but you take one thing from each and every column, multiply it out, and figure it out that way. Going back in time. I was finding the least common multiple of the first one we did. 3, 5, 2, 7. Figure out what all of those are, and you'd be good. Should be 210. It would totally be 30 with a 7 on it. 7 times 3 is 21, so I'd throw a 0 on it. Is that cheap? I think that's cheap. I don't care though. Totally 210. All right. So, yeah, conceptually, not bad, right? Not bad. So, what's useful is that least common multiple. As I said, that's the same method we already use if we are combining fractions. And we'll find that that's generally the tough ones that we'd have to do for these. I hate all of these. Hate all of these. It's a very accurate meme, by the way. I was in Jack in the Box at one point, had my headphones on, but they're bone conduction headphones, so I could still hear out of my ears, no problem. I got them for riding my bike around town so I don't get run over. Elderly couple has both of their phones on full blast. Guy hanging out in the stall over here is like, okay, what? I don't even know what was going on, but he was on hold with the company and then asked for a ride. It was weird, but it was all very loud. And even though I had headphones on, couldn't freaking hear him. Hated it. Not happy with my examples here. Not happy with them. What can we do? We already got the method down, right? Not bad. Should we play with applications and fractions for this? That's 90% of what you'd be doing. I'm not doing for these. Play with applications of fractions. Then I gotta figure out some good fractions. You know what? Got some good fractions. Let's start with number 3. But we're gonna play with this. Instead of 24, 11, and 14, we're gonna have 5/24 plus 11, or you know what? Yeah, whatever. 11/14 plus let's roll with the joke again. 7/11. Let's do that. Let's say we have something like that. Suddenly we have to add them together and it's like, oh God, what am I going to end up using? So I'll show you how I generally do lowest common denominator. It might not work for you guys. This is the way that I would try to tutor with it and it wouldn't always stick. So if it doesn't, use the weird chart thing, okay? So I would do the usual. I would factor all of these guys down. 11's kind of cheap because it's literally just 11. I factor all of these guys down. And this is kind of funky. What I would do is I would start with the smallest number and I would look at each individual term, the 24, the 14, and the 11. And I would say, okay, whichever one has the most amount of those 2s, that's how many we're going to go with. So that first guy, the 24, has 3 2s on it, right? The second one, the 14, has 1 2. And the 11 obviously doesn't have any. So what's the most amount of 2s that any of these individual terms have? Well, that first one had 3. So our lowest common denominator has to have those 3. Then I look at my next number up. Now this isn't a great example for this type of problem because this one's a 3. Anybody else have a 3? No? What's the most amount of 3s any of these have? 1. Well, I need it. Then the next term. This one has a 7. Anybody else have a 7? No. But we need it. Because we are getting the smallest thing that covers all the factors across everything. Last one's 11. Yeah, we need an 11. So if I do that big, ugly chart, this is what would be at the bottom of it. Because if I look at the 24, it's 3 2s and a 3. 3 2s and a 3. Okay, we have that covered. What about 14? 2 and a 7? Yeah, we got those in there. 11? Yeah, we got all those in there. So everything's represented. Now we can multiply it across. And we get 1,848. Does anybody need to see the other method of doing that? The chart thingy? Anybody need to see the chart thing? Help anyone. Give people a chance to type just in case. Oh, I guess that helps if the whole thing goes on there. Not bad. Okay. Well, that's pretty much an application of the least common multiple, right? So if I was to add these guys together, and I am aware that I just made a horrifying, terrible problem. I am sorry. Really, it's the 11 that's doing it. Well, I would have to multiply each of these by whatever gets my denominator of 1,848, right? I don't like that, right? You guys like that? No? Maybe? I don't know. Well, the nice thing is that, kind of like I showed you earlier, if I'm trying to figure out what this one needs, I don't really need those guys, right? I don't need these. We already got those. So it needs a 7 and an 11. So this one I can multiply by 77. Top and bottom. Now let's say you don't like that idea. You're like, oh God, how did he just do that? How am I supposed to do that? If I'm in a test, how the hell am I supposed to do that? You don't have to. Another way of doing it is, well, if I'm trying to get 2 here from here, you just divide this by that, right? 1848 divided by 14, I get 132. I have to multiply this by 132 over itself. Hey, you know what the 11's about to get? All of that. That 24 times 7, 168. That is how many hours are in a week. Ideally, you spend 1/3 of that sleeping, maybe probably about 1/3 of that working. 1/3 of those hours you might get to enjoy. You probably won't, but you might. Isn't that great? Man, we invented fire, and what did we do with it? We got freaking credit scores and we got rent. Fire, we just discovered. Okay, so we're going to multiply across top and bottom on all of them. Not the prettiest problem in the world, but you know what? Made my bed and I'm going to sleep in it. So multiplying across, this ends up 385 over. And for each of these, I'm actually going to do the multiplication to make sure that I get that common denominator, because if I don't, I made a mistake somewhere and I got to go back and fix it. So that's kind of like a small check for me, is multiplying that out. 7 times 132, 1452 over 14 and 132 is, yep, 1548 plus now, more likely, I will say in the future, more likely, instead of big numbers, you would be doing these with weird looking algebra functions. I don't want to throw those at you right now because, okay, they're simpler, but they're also something you haven't seen before. And we definitely don't want to start throwing piles of binomials at you. Okay. Well, we're adding fractions. We got a cross on top, 385, 1452, and 1176. 3013. That doesn't sound like something that's going to break down nicely, does it? No, no, those numbers do not have a single factor in common. So you know what? That's our answer. Isn't that horrible? It's great, isn't it? Yeah. If I'd actually, worked out this problem to have some neat, nice little numbers that go together, then we'd end up with an answer that doesn't look horrifying and quadruple digits on top and bottom. But such is the problem of making up problems on the fry. On the fry. Right. I don't know where I'm going. Very tired. Have to go to bed soon. To wake up at 4. Let's see. What else could we do? What else could we do? Let's do something terrible. Well, see that I like that. I don't know if we want to do that sort of thing quite yet, but I like it. Something with more than 2 terms. Come on, guys. Okay, so this sort of thing, algebra-wise, I like this image. I don't like that it's a video, but I like the image. This is the sort of thing that the concept will eventually apply to, because you break things down as far as they can factor, and you end up using that common denominator to put the big ugly things together, right? That's really what we're going to. I don't like any of these examples. People suck. Going to oh, that number sucks too. I don't know, I don't like any of them. All right, so to avoid what we just ran into, let's just do them as written. Let's do a couple more. Do number 9 and number 10. I don't think we want to get into the next stuff quite yet. I don't want to cover on that. So in this case, I'm going to go ahead and find both the greatest common factor and the LCM, these common multiples. We're going to find both of them. That's a fun way to do it, right? It's easy enough. Works the same on both, right? So let's break them each of them down. So the 108 gonna be cheap and kind of go under my work here. So that's 2 and 54, which is 2 and 27, which is 3 and 9, so 3 and 3. And then 15, I like 15, 3 and 5. I like 15. Okay. Do it just off to the side here a little bit. So do the exact same thing we did before. We have a column for each thing. So 15 is the easy one. We do that one first. That one's 3 times 5. So column for each of those. And then the 108, that doesn't have any 5s. It just has a bunch of 2s and a bunch of 3s, right? We already have 1. But we need columns for the other 2 3s and the 2 2s. 2 2s, 2 3s. Okay. Wish I had just written that slightly over. Okay. So it's greatest common factor. That one's real nice. What is it? What do they have in common? It's covered by both. 2 and 3. Not a 2 and 3. We're gonna have another 2 and 15. Just 3. That's the only thing they have in common. But what about the LCM? The LCM takes one thing from each and every column. So you have that 3, then a 5, 2, 2, 3, and 3. What is that, 540? 3, 2, 2, 3, 540. How are we feeling on GCF and LCM? We're okay, slightly concerned, tolerable. Anybody online having issues? Speak now or forever hold your peace. The peace as in P-E-A-C-E or peace as in your peace of mind. P-I-E-C. Forever hold your peace. I'm voting peace of mind. Basically means just shut up and keep it to yourself. Okay, so nobody's freaking out. I'm going to assume we're good on GCF and LCM. And 15 minutes ain't long enough to cover. How many slides do I have on exponents? I'm not going to do is all the. We're going to have to make some algebra problems, aren't we? Yeah, these are too easy. We can make these worse. I love this comment. Hey, do you know why they call them the Dark Ages? Because of all the nights. You get it? It's a great last word, you know? Stupid joke. Wonder how many people died in the South saying, hold my beer and watch this. I think a lot. All right, well, I feel like we're good. I feel like we're happy. We're happy here at a stopping point, right? I'm happy here as a stopping point. I'm gonna round it to 8:30 so I get paid. Now, this is recorded. So if anybody notices that, I could easily be fired. But I feel sick. I don't think anybody's ever gonna watch that video. So you guys all have a good night. Not this kind of night, not the kind that guy's talking about. I will see you guys on Thursday, where we will do exponents and scientific notation and roots and radicals. And then I might just find some random problems on the internet for us to do algebra wise. It'll be fun. Yeah? Yeah. Cool. Go home. All you people online, you're probably already home. I envy you. No water outside, so I'm happy. All right. Have a good night, everyone. Thank you.